Good morning, good afternoon. My name is Scott Best. I'm a product manager here in Rambus Security. And today I'm going to be talking about memory encryption solutions for protecting data in use. I can't take any questions directly during the presentation, but I think questions can be posted into the platform in the chat. And also this presentation will be available in PDF form from the portal when the presentation is over. So without further ado, I'm going to jump into it. First of all, to start with an introduction, memory security is a huge topic, so I thought I would take it apart, both in the sense of what do I mean when I say memory, because memory, of course, means many different things. Everyone here on this webinar probably has a different understanding of what memory means, and of course, security also means many different things. So I'm going to walk through what I mean by both of these. And then I'm going to pick on a couple of examples and go a little deep into those details. So starting with memory, the first most obvious form of memory is the on-chip SRAM that might be inside of an SoC. And this is, of course, the scratchpad cache memory of the apps processors within an SoC that are doing, the high performance calculations, the thing that the CPU needs as its fuel to execute the code space. That's one form of memory. Another form of memory is on-chip non-volatile memory for long-term storage of the firmware associated with those SoCs, apps processors. This could be embedded flash, this could be MRAM, this could be some form of fuse, anti-fuse, one-time programmable memory, lots of different versions, depending on where you're manufacturing your SoCs for on-chip non-volatile memory. But another, of course, totally valid version of memory with security implications. The third one is off-chip non-volatile memory. This is long-term storage of high-level OS runtime applications, relatively large amounts of data on the order of hundreds of megabytes, gigabytes that are necessary for execution of the system application as it's running. So not something that is feasibly, stored in a long-term sense on chip. It is stored off chip, and of course, when it's off chip, it has different security considerations than something that is on chip. And lastly, at least for purposes of this presentation, I'm going to discuss off-chip DRAM. This is execution memory for the SoC CPU after transactions have been evicted from last level cache. Last level cache, of course, being performed by that first bullet, that on-chip SRAM to scratchpad memory. All right, so those are the four types of memory when we're describing a system. Again, they all have different security considerations because they all have slightly different attack surfaces. So I'm going to go into what I mean when I say security now. The first type of security is the most obvious one. This is data privacy. You don't want your adversaries, in a lot of cases, snooping on what the contents of memory are. That might have private data, it might have secret keys, it might just have application code that you would wish to remain proprietary throughout the duration of a system's execution. So data privacy is, of course, the first and most obvious form of data security, but there's also data authenticity. If an adversary gains control of one of those memory systems, how do you prevent them from injecting modified data into the CPU? You can very quickly imagine how bad the world gets if your adversary has write control over some of the data and the CPU is just going to grab it, execute it, and not in any way verify it for authenticity. So data authenticity is the second pillar of memory security. And lastly, there is data freshness. This is if your adversaries have found that you not only you're implementing some data authenticity, but you've also updated a system from one state to another state. Now an adversary might be able to, if they're very sophisticated, go and grab an older copy of valid data and now inject valid but old data into a system for execution. And this can cause problems in different ways than completely malformed data, but it does allow for some interesting injection attacks. You can trick a chip, you can trick a system into thinking it's in a different execution state, perhaps a debug state, and not a more secure mission execution state. So data freshness is the third pillar of data security. Probably every single one of these topics deserves its own webinar, but for today, I'm going to focus just on two of them. So I'm going to pick those two use cases. So I'm going to first discuss off-chip NVM, long-term storage of the OS, the runtime applications, maybe the training sets, the data sets that, on the order of gigabytes of data that are being stored off-chip, and also off-chip DRAM, because there's some very interesting complexities there. And from the security point of view, I'm going to just discuss today privacy and authenticity. I'll speak to freshness when I get to authenticity. Freshness has some very obvious solutions for it, and as is often the case, the obvious solutions are the most difficult ones. So I'll speak to that a little bit when I get to the data authenticity part. So moving on, I'm going to go into the first use case now, and the first use case, again, is over here on the left. I have some sort of high performance compute. This might be a classic x86 server with lots of servers, lots of blades. It might be a chiplet inside of an SIP, and it's the high performance portion of that SIP that's performing the major compute. It might be an SoC based FPGA. There's lots of reasons that you would have high performance compute over on the left, and mass storage over off-chip, mass storage over there on the right. And it, again, might be storing the OS firmware. It might be storing the runtime code, the application space that you would wish to remain proprietary. It could just be the SoC's bit file. There's lots of reasons why you would want the data in that piece to be secure. So between the two is this big blue cartoon. And for now, I'm just referring to it as a high-speed secure channel. And what we want here is tamper-resistant encryption and tamper-resistant authentication. I'll go a little bit into what I mean when I say tamper-resistant. Of course, encryption and authentication are good. It's a great start, but of course, your adversary is no novice at attacking encryption and authentication. So having some degree of tamper resistance is essential. So I'm going to make this picture a little more complicated. So now what is servicing? What is the actual circuitry, and where does it actually reside? So this blue box is now turned into, perhaps it's an inline FPGA, perhaps it's a circuit on an ASIC, perhaps it's a circuit on a chiplet. And this is now serving as that high bandwidth bridge between the processing on the left, mass storage on the right. And you want this to be high bandwidth. You're pulling in gigabytes of data. There's several different threads that are pulling on that data, so you want multi-channel crypto. And again, for the security concerns, we both want data privacy and data authentication. So perhaps something like high-speed AES GCM is the appropriate crypto protocol used to do that. So right now, it appears to be a sufficient solution, right? We have the high-speed wire, we have the high-speed AES GCM, it's multi-channel. But we've really only now moved the problem in an interesting way, because we also have to worry about key management. I mean, crypto is relying on, of course, obfuscating data based on some key material. But if your adversary can obtain that key material, it doesn't provide any security at all. So how is this proposed solution managing the keys? And also, how is it handling transaction control? There's a lot of data, there's a lot of threads. So there's some sort of what's colloquially referred to as DMA. It's not DMA in the traditional sense, but it's DMA in the sense of you need something to program what the transactions controls are, what the granularity of access is, and be able to program those pieces so that those multi-threads running in the HPC environment can pull data over high-speed wires at wire rate off the NVM and the mass storage. I've also updated the box to indicate, yes, this should be tamper resistant, high bandwidth crypto. And a good example of tamper resistance is DPA protection. That is differential power analysis protection. This is a type of attack, as I'm sure has been explained in other places today. This is a type of cryptanalysis attack where an adversary can recover key material just by carefully monitoring the power supply or EM emissions of a chip as it's performing encryption and decryption. And key material can leak information if it's carefully monitored. So of course, it's required that the encryption and decryption be mitigated from that, have countermeasures for handling that type of power analysis attack surface. So I've updated this box now. Again, it's tamper resistant, high bandwidth crypto that is DPA protected. And again, it's running the AES GCM algorithm, which services both the data privacy and the data authenticity. So getting back to my originally stilted question, what is servicing this key management in DMA? And now what I'm going to demonstrate is what a full solution would actually look like. There's that high-speed wire again, the tamper-resistant crypto, and now we're using a root of trust, also known as a root of security or a trusted execution environment or an embedded HSM. There's a lot of things that act as a root of trust, and they're essential. They're essential not only for self-booting this environment, this inline FPGA or this ASIC or this chiplet, but they're also the thing that does the key derivation. So it receives key seed material from a variety of system sources, and it generates these ephemeral keys on command, and those keys are what are used to encrypt and decrypt the transactions that are moving in the high-speed wire. Those keys don't exist in the system in any long-term sense. They are derived as necessary, and they're derived in tamper-resistant ways. So even if your adversary were to capture one of these systems and take it apart, they don't have the clearest ways of determining what the keys were associated with that, because the keys are not stored as other insecure data might be stored in any long-term clear text sense. It derives that data. It derives those keys in an ephemeral sense from on-system key seed sources, as shown. Once you also have a root of trust, of course, you can now have a place for doing the sensor fusion of actually looking at the alarms and sensors in the systems, things that are actually detecting whether an adversary is using the system correctly or incorrectly, and take evasive actions if necessary, because a root of trust is often a programmable environment, and it's up to the system implementer of how much of that sensor fusion will be done inside of this system. And of course, we recommend that a lot of that be done inside of the system. And secondly, I've now shown thirdly, perhaps, I've shown a DMA engine here. Again, this is the programmatic object that is used that receives control information from the root of trust system to be able to schedule those transactions through the wire. So this would be what I would consider a sufficient first-class solution for memory security for off-chip NVM storage. I'm going to summarize this use case now. Again, off-chip NVM, long-term storage of everything you might want to keep private from an adversary were they to recover the hard drives or off, the NAND flash, whatever it is that if your adversary were to recover that long-term firmware from your system, what would you not want them to see? That is this use case. And the security concerns that were mitigated here, I discussed the data privacy. You want that to conceal the particulars of the OS. Perhaps there's an attack if the adversary knew exactly what some of the weaknesses were in the kernel objects that you're using. There could be proprietary application code in there. There could be data as IP objects in there. And secondly, there's that data authenticity part, preventing your adversaries from tampering with your system by modifying that data and then having the system pull that in as if it were authentic. AES GCM is a good low latency solution that, of course, can layer on top of other types of signature verification, asymmetric algorithms that are much slower, much more computationally intensive, but they can verify large amounts of data to verify that they are unmodified. AES GCM is a good low latency solution that can verify as it's pulling data in. And those two, I think they're synergistic and combine together pretty well. All right, so that's the end of the first use case. And I'm going to press forward here into my second use case, which is similar, but in some ways entirely different. And that is off-chip DRAM, which, as most of you know, is the execution memory for your SoC CPU after the transactions have been evicted from the last level cache of the system, and they're now sitting. It's considered sort of an execution memory. It's an order of magnitude slower than on-chip cache memory, but it's a good place where execution, application code, OS objects are stored in the DRAM. And for the same reason as the NVM, there are data privacy concerns. You don't want the adversary snooping on the contents, and you certainly don't want adversaries from injecting modified data so that the CPU picks them in and begins executing without authenticating the veracity of that data. Here's a cartoon that describes what inline memory encryptor for a DRAM system might look like. And this begins to describe why the system, why an IME, an inline memory encryptor, is so much more complicated in some ways than other systems. Again, obviously, it's protecting the data between the CPU and the memory, solving both the data privacy and data authenticity parts. It's essential to the system because, as I've shown in this, the DRAM module is removable, and it's meant to be removable. It will lose data temporarily while an adversary might be picking it out, but there's dozens of gigabytes on a state-of-the-art DRAM module, and a lot of that data will persist, especially if temperatures can be managed pretty carefully. A lot of that data will persist. There's a lot of remnants in there before a module can be picked out of a live system, dropped into a power restorer system, and most of that data will remain. There's also inline bridges that can be inserted between a DRAM module and the DRAM system, and you can pull out live traffic while the DRAM module is actually working. Of course, this requires physical access to a system, but in a lot of cases, the adversary does have physical access to a system, and they can just put in inline debuggers between the module connector and the DRAM connector and actually look at the data. I mean, they're fantastic products, and they can be misused. So DRAM has that interesting challenge that it is a removable module that can be monitored in situ. It's also more complicated than other inline crypto because there's this concept of cache and coherency. I'm going to speak to that a little bit later, but in general, what I mean by that is that when a CPU is performing transactions on the data, there's level 1 cache, there's level 2 cache, there's last level cache, then the data is evicted, goes to the memory controller, usually without an IME, goes to a memory controller, the memory controller schedules a transaction through the PHY into the DRAM. The system knows the entire time where in that memory hierarchy the data is actually valid and authentic and most recent. And that's the point of coherency. And you can imagine it like a small golden ball that's moving through the system, and the system knows to ignore different stages of cache and to go for the data here. So if you insert something between where those points of coherency are, then you become that point of coherency. And you have to be able to manage that. So an inline memory encryptor is not just performing the crypto, because there is a chance that while a write transaction is being serviced and it's in the middle of a crypto pipeline, and access for that data shows up. And the data is not yet even being encrypted, never mind then decrypted and returned to the system. So there's a necessary aspect of caching and coherency that an IME needs to be able to service. It ends up being a lot more of a complicated memory block, a complicated crypto block than the first use case, but it's a fascinating solution space to work in. The other part about IMEs that's tricky is they create metadata. This is metadata, data about data. This is, for example, those authentication tags that as the CPU is writing data, the CPU does not know that the IME is going to be creating an authentication tag that is then used to check the authenticity of the data when it's subsequently read. That tag memory turns out to be a lot of memory. It's several bytes of data for every cache line access that's moving. And where is that data actually stored? It's stored in the same DRAM that the live data is stored in. So there's a necessary partitioning of the memory space. And that partitioning is either, it's done spatially, it's written into separate pages, or it's done in serial order. So you're extending the burst length, but somehow the memory controller needs to be configured to allocate an amount of memory to the IME so that the IME actually has the ability of writing this metadata into the DRAM system. And then during a read operation, the IME has to be smart enough to go grab not only the data, but grab the metadata that authenticates the data read. It's a lot more of a complicated system. It requires a lot more coordination and configuration of the memory controller. It's a little bit more challenging than the first use case, but challenging is good. So I'm going to go into a little bit more detail now about some further challenges and then present one of the solutions. What I'm doing here is I'm breaking a DRAM system topology. I'm categorizing all DRAM systems into 3 topologies. This is completely unfair, but I can carry it around in my head. The first one is a server class CPU-based memory solution. So this might be a server blade sitting in a cabinet of blades in a data center of thousands of cabinets. These are very large memory footprint systems. They have dozens of high-capacity DIMMs on them. The emerging CXL-based systems that are being discussed elsewhere in the RDS today are extending this capacity. These are very large systems, and you can imagine that configuring the memory controllers for this system and handling the latency aspects of this system are a much different problem than if you have a much smaller amount of DRAM. So that goes into the second one. Now, this is more of a small board computer system. It's still ASIC based, right? So there's still an SoC, but there's a small to medium amount of footprint, maybe a single digit number of channels, small number of DIMMs. In this solution, it's a little more challenging because when vendors are building an SoC that's going to talk through a DRAM PHY and onward to a DRAM, they have a lot of choices of which DRAM PHY vendor they're going to work with, or if they're going to build it themselves. They also have a lot of choices of which memory controller they're going to use to talk to that PHY. And there's a lot of choices of vendor there, including, of course, Rambus. And every one of those memory controllers is, of course, slightly different. They all have to do the fundamentals correctly, but they all have different performances. They're all configured slightly differently. They have different aspects and performance aspects to them. So you can imagine now the challenges here of it's difficult to build a single IME crypto block that is immediately compatible with every vendor's memory controller. Right, there's a little bit of coordination that needs to occur to be able to customize the crypto block so that it is compatible with every one of those versions. Whereas in the first case, there was one memory controller. This might be, for example, the memory controller that Intel might use on a Xeon class-based server that they have. And it is the same memory controller throughout the CPUs. It is one IME design that is compatible with that. It's different in that second one, just given the vendor diversity. And the third box that I'm going to throw into this are FPGA-based systems. Again, small memory footprints like that first one, but these, especially with the new emerging SoC-based FPGA platforms, which combine both hard logic CPUs with programmable fabric, those tend to have hard logic memory controllers as well. There's a number of FPGA vendors out there, and as you can imagine, similar to the second case, they are not, they configure differently. They're slightly, the diversity of vendor there is similar to that second issue. These systems are prevalent in US defense systems, given what the volume of those systems are, and usually in a defense deployment. And also the IME in this topology does not exist in hard logic. Usually the IME solution for this now exists in the programmable fabric. So you have to now modify the FPGA connectivity so that the hard logic processor talks to the hard logic memory controller via the user fabric, which might not be what it was originally intended to do. So this is why I characterize these 3 topologies as different opportunities for IME deployment. Here's an example of our first launch into this space. It is our initial IME product effort. As I've been describing, it requires both crypto expertise as well as memory expertise, because you have to handle the cache coherency. You have to handle what happens during sub-cache line access for this circuit to now perform read, modify, writes. Low latency is of course essential, but you also have low latency metadata grabs because you have to be able to pull GCM tags to authenticate the reads that you're performing. Freshness counters can also fit in here. Freshness, as I described very earlier, it's another type of metadata, but there's a lot of counter space. Where are all of those counters being stored? How are they being stored? And of course, while you're performing the crypto, remember the crypto? While you're performing the crypto, you want tamper-resistant crypto, including both power analysis and fault injection attack resistant crypto. Rambus's initial product in this space is for that third bucket. It's for FPGA platforms. And we're offering this in partnership with Idaho Scientific, who's been one of our long-term partners in FPGA solution space, especially for the US defense industry. So in summary of that second use case, off-chip DRAM, it's the execution space. It's a very challenging space to be able to insert crypto without breaking the system. The system so wants to break when you insert something in the middle of it. It's difficult to do well. The data privacy should be DPA protected to protect against those power analysis attacks. It can optionally be protected also against fault injection attack. And this type of crypto path is also a potentially really interesting use case for emerging lightweight crypto standards, Karma Prints, ASCON, et cetera. Not quite as heavy or as LUT heavy as full bore 10 round AES algorithm might be. So it's an interesting use case for lightweight crypto to solve the data privacy problem. And the second case, of course, the data authenticity and handling the metadata allocation through the memory controller, especially in these small resource constrained systems. All right, so that's everything I think I had to talk to you about today. The PDF again is going to be available on the portal. You can post questions into the chat, and there's an AMA, I think, scheduled after this, so we're going to be on that. Today, I talked about the off-chip NVM long-term storage use case. I talked about off-chip DRAM execution, the IME challenge of implementing that, covering mostly data privacy and data authenticity. Again, every one of these use cases is sufficient for its own webinar, so please push any questions you have. My contact information is there. Thank you very much for attending, and thank you to all of my colleagues who helped in support of preparing this content. Appreciate it.